Copyright University of Auckland, all rights reserved. The content and delivery of lectures in this course are protected by copyright. Material belonging to others may have been used in these lectures and copied by and solely for the educational purposes of the university under licence. You may record the lectures for the purposes of private study or research, but you may not sell, alter, or further reproduce or distribute any part of these lectures to any other person. Failure to comply with the terms of this warning may expose you to legal action for copyright infringement by the copyright owner and/or disciplinary action by the university.
No mai piki mai, kake mai, ki te rohe o whare walanga tamaki makoro. Good evening and welcome. My name is Professor Frank Bloomfield, Director of the Liggins Institute, and it's my great pleasure to invite and welcome all of you here tonight. It's fantastic to see so many of you on a cold night like this, although fortunately it's not raining, which is always a great benefit. So most of you may be more familiar with the Liggins Institute because of its research into mothers and babies and how the early life environment is so important for our lifelong health. But of course, if it is important for our lifelong health, that means that we are also interested in health throughout life, because we want to know how early life events do impact upon us as we age. So this evening we're going to hear about from three of our key researchers who are investigating how health later in life is impacted on, particularly by genes, diet and the environment. And for some of our Institute researchers, particularly the second of our three speakers this evening, the importance of health that is around the midlife crisis is of particular and personal importance. So from beating breast cancer to choosing foods that preserve muscle mass and prevent inflammation, all three of the researchers you'll hear about tonight are passionate about transforming scientific research into health benefits, particularly around the midlife health issues. So you'll hear from Joe Perry, who is developing a new cancer drug that could improve the effectiveness of radiotherapy, and will explain why blocking the growth hormone receptor is important for this outcome. Professor of Nutrition David Cameron Smith will explain how our nutritional needs change as we age, and how the right diet and exercise can help you maintain muscle mass and strength in your mid and later years. And then we also know that food intolerance is more likely as we age, and so we'll finish the evening with presentation from research fellow Dr Amber Milan, and she'll explain how we identify the components of foods that cause problems and present some of the possible solutions that her research has discovered. But before we get on to our speakers tonight, just a few housekeeping notes. The exits are through the doors that you came in, or the two doors at the front, and if there is an emergency, then you'll be made well aware of this by flashing red lights and very loud sirens. And so if these do go off, then please exit the lecture theatre and congregate just outside the main doors that you came in. Bathrooms are located out in the foyer and also off to the right. And please do turn your cell phones to silent or off completely. Thank you. So to kick off this evening, we have Dr. Joe Perry. Joe Perry is a senior research fellow at the Liggins Institute, and she's interested in cancer cell biology and the involvement of hormones and growth factors in the progression of cancer, particularly breast cancer. Joe completed a PhD at the Institute for Cancer Research in London and was awarded a National Health and Medical Research Council Peter Doherty postdoctoral fellowship at the Murdoch Children's Research Institute, so a very prestigious fellowship to a very prestigious institute. Joe joined the Liggins Institute in 2005, where she and her research group investigate the interactions of human growth hormone with cancer therapies. And in this evening's talk, she will describe some of the risk factors and treatment options for breast cancer, as well as presenting some of her exciting new research into the role of growth hormone in the development of cancer and how blocking it could improve the effectiveness of radiotherapy as a treatment. Thank you, Jo.
Thank you very much. Kia ora and welcome, and thank you very much for coming out on this very chilly night. So as you've heard about, we're going to be talking about breast cancer tonight. And the work that our lab is doing at the Liggins Institute is really interested in some of the hormones which contribute to cancer cell growth. And we're interested in one in particular, that growth hormone. So we're particularly interested in, we've been able to show that they promote cancer cell growth, and we're particularly interested in taking advantage of this to perhaps develop therapeutics which will be able to treat breast cancer at a later stage. But before I get onto this work, we're going to talk about breast cancer and talk about some of the risk factors which are associated with it. So breast cancer in New Zealand is the most common cancer in women. 1 in 8 women will get this disease over the course of their life. Of course, breast cancer doesn't only occur in women. In New Zealand, we get more than 3,200 cases every year reported in women and around 25 cases in men. So men tend to present with a more advanced form of disease. So they present at later stages where it's sometimes more difficult to treat. So it's really important to be aware of that. In New Zealand, we have a higher incidence rate in Māori women and a higher mortality rate in Māori and Pacific women. Worldwide, it's a major cause of cancer-related deaths in women, and in New Zealand, there are around 600 deaths every year associated with breast cancer. It only really takes me a few moments to reel off these statistics, and I do it quite frequently in my talks. However, it doesn't come close to reflecting the impact that this disease has on patients and their friends and family. So the breast cancer incidence across the world varies quite significantly. There are actually quite high rates in certain areas, as you can tell from these dark blue areas. So we've got higher rates in North America, higher rates in Europe, and also very high rates in Australia and New Zealand. Lower rates are seen in Asia and also Africa, but we're beginning to see an increasing incidence rate in these areas as well. This is New Zealand data, and there's been quite a significant increase in the incidence rate for breast cancer over recent decades, since the 1950s. But the key take-home from this graph is the fact that that mortality rate has been declining. And in fact, it's decreased by about half since the 1990s. And that's, of course, as a result of the fact that we've got better ways to diagnose it and better ways to screen for it, and we've got better treatments, which is great. So there are a number of risk factors which are associated with associated with breast cancer, and we're going to go over a few of those. Of course, apart from being female, the majority of cases occur in women over the age of 50. That's around about 70%. But as you can see from this graph, it's possible to get it much earlier on in life as well, and that's important to be aware of. Even in your 20s, it's just much more rare. Also, at the other end of the scale, it's important to note that you can also get, so our free screening program in New Zealand finishes at the age of 69, but it's also possible to get breast cancer much later on, and that's important to be aware of. There are a large number of risk factors which have been described for breast cancer, and we don't have time to go into this tonight, unfortunately. I'm happy to speak about it at another time, or on it at another time if needed. I'd like to highlight a few though. The first of these for reasons for the fact that actually it's quite a small amount of cases which are associated with this, and it's family history. So around 5 to 10% of cases are associated with genetics or family history, but it's actually quite small, and the majority of cases of breast cancer will have no family history associated with them. Another key risk factor is our lifetime exposure to estrogen, and there's a whole host of risk factors which are associated with this. So this hormone estrogen plays a really important role in the development of the breast during puberty, but it's also contributing to, it's a risk factor for breast cancer, and it contributes to a large proportion of cases. Around 2/3 are classified as hormone responsive, so they're responsive to this hormone estrogen. Key risk factors which are associated with are these. So going through puberty earlier and going through menopause later, that increases your lifetime exposure to estrogen. We're having fewer children, and we're having children later on in life. And having more children and having your first child earlier on is actually protective. So the hormone replacement therapy, which is used to treat symptoms of the menopause, is also associated with a slight increased risk, as is the oral contraceptive, but that risk is small associated with that. So we're going to touch on some of the risk factors so many of these risk factors you can't modify, they're not modifiable, but there are some that you can do something about, and we're going to touch on those at the end of this talk. So patients who have breast cancer will undergo various treatments. Most will undergo surgery, a large proportion will undergo radiotherapy, and there's also a number of drugs which are available. So those patients with hormone-responsive breast cancer, so it's responsive to estrogen, will be treated with a hormone therapy which blocks estrogen from working or blocks the body from making it. There's also a range of chemotherapies, but some of the major advances have occurred in the targeted therapy space. And just to explain what I mean by that and to distinguish between these two, you're probably quite familiar with chemotherapy and have heard about it. Chemotherapy works by targeting or affecting rapidly dividing cells. And for this reason, it can affect cancer cells, but also normal cells, and is quite often associated with some quite significant side effects in patients. Targeted therapies exploit vulnerabilities in cancer cells or target specific molecules or the genetics of a tumour. And for that reason, they're more likely to focus on the cancer cell and have fewer effects on normal cells. Of course, all of these therapies have some degree of side effect which is associated with them generally. So these targeted therapies allow clinicians to target a treatment to the genetics of a patient's tumour. And this type of personalisation is possible due to the rapid advances that have been occurring in genetics in the last few decades. So in 2001, the sequence of the human genome was first published. So this was the draft or decoding the entire DNA in a single cell. So this actually took 13 years and it cost $2.7 billion. But if you jump forward to today, we can now sequence the genome in around 3 days for under $3,000. And the impact of this has been huge. It's led to additional projects. We've gone through the 1,000 Genome Project, and we're now in the middle of the 100,000 Genome Project. And the amount of information we're getting from this is massive. And a large focus has been on decoding the genomes of cancers and specific types of cancer. And this has allowed researchers to identify some of the mutations and genetic variation which is driving this cancer growth. And this has led to advances in diagnosis, prognosis, and also in treatment. We're beginning to see this come through the clinic now. So there have been a large number of drugs which have been approved for treatment for breast cancer recently. These are the target and hormone therapies which have been FDA approved. There's also a whole host of chemotherapies. There's a whole lot more coming through clinical trials as well, which is great. And clinical trials looking at ways that you can combine these drugs to improve outcomes for patients. But despite these advances and despite the fact that we've got declining mortality rates, we still can't treat every breast cancer patient effectively yet, and particularly not for those with advanced disease. And the reason for that is that breast cancer is not a single disease, or part of the reason for that is not a single disease. So we talk about breast cancer as though it's a single entity, but it's actually a really complex group of diseases. There's many different types of breast cancer. And if you take two tumours which are very similar and from two patients which have the same type of breast cancer, and you look at the genetics of that, it can actually be quite different. And you know it's going to be complex when I put up a figure like this and then I try and explain to you. So what we're looking at here is the analysis of almost 2,000 genes across around 200 tumours. Each of these vertical lines here is actually an individual patient's tumour. And what you're looking at is these patterns, and these patterns are genes which are turned on or turned off in these tumours. And without going into the details of this, because it's a really complex technique, basically I'm hoping that you can see in this image that there are different patterns across here. And there are clusters of tumours with similar profiles. And these clusters are actually different types of breast cancer. And this type of analysis picks up more types of breast cancer in research labs than we do actually classify in the clinic at the moment. Also, if you take one type of breast cancer here, I hope you can see that there are similarities across it, but there are also quite a lot of differences. And some of these differences that are occurring, or this genetic diversity in these breast tumours, is going partway to explain why perhaps two tumours from the same patient with the same type of breast cancer can be treated with the same drug and potentially have different outcomes. This type of analysis is not used routinely in the clinic yet, but eventually it will. But we are beginning to see the benefit of this, and this is in terms of some of the genomic tests which are becoming available. There's a whole lot of these which are becoming available or are currently clinically approved. I'm just going to highlight two. So ProSigna has just become available in New Zealand very recently, and also Oncotype DX. So these are used for early stage breast cancer, hormone receptor positive tumours, and they're used to predict which patients, or to help clinicians determine which patients might have more chance of their disease recurring later on, and which patients might benefit from chemotherapy, or might not need chemotherapy, which is also great. So another reason that cancer has been difficult to treat, and another thing which is impacting on treatment, is the environment that the tumour grows in. We know that the tumour is not just made up of cancer cells. It's actually made up of a whole lot of other cells. Here's our cancer cell here, but we've also got immune cells, we've got fat cells, and we've also got cells which lie in the blood vessel. Now these cells are not in isolation. They communicate, they talk to each other, and they interact with each other, and they do that by producing and secreting hormones and growth factors which act as messengers to the cells around them. So we still don't really understand how this works, and these communications between cells can facilitate the tumour growth, but also it can impact on therapy. For instance, some of these factors get upregulated under stress conditions which the cell is faced with. For instance, if it's being exposed to cytotoxic drugs. So we don't really understand how this works yet, but this is one area that our lab is really, really interested in. We're interested in how these cells are communicating, and we're interested in the hormones that they're producing. So one of the hormones we've been working on is, of course, growth hormone. And it's going to come as no surprise that growth hormone is the key regulator of how tall we grow. It's a key regulator during childhood and also in puberty, and we've known this for decades now. It was first identified in the early 1900s. As well as being essential for growth, it also plays a really important role in a whole other series of physiological functions around the body. We absolutely need normal growth hormone levels for normal growth, but having too much or too little is associated with growth disorders. So too much during childhood leads to gigantism, and too little leads to short stature and growth conditions such as in Laron syndrome, and we'll touch on them shortly. There's also conditions in adults, but there are also a number of medical therapies which we can use for treatment of these types of disorders. So this hormone is produced by a small pituitary gland which is found at the base of the brain. It's released into the circulation and it circulates around the body. It impacts on a whole host of different tissues. As well as being produced by the pituitary, though, we also know that it's also produced at other sites around the body in local tissues and has local effects in the tissues it's produced in. We have very high levels of growth hormone as we're growing and during puberty, but those levels drop off as we age. And that could be for good reason, because it's become apparent that decline in growth hormone, or it's become apparent that that growth hormone is intimately linked with cancer development. And some of the most striking evidence for that comes from a large number of animal models that occur naturally in nature, where growth hormone deficiency leads to animals which live longer and also get less cancer. So this little mouse on the right-hand side is an Ames dwarf mouse. And apart from being very cute, it's also a lot smaller than the otherwise genetically identical mouse sitting next to it. So this mouse is small, it lives a lot longer, and in fact, it's one of the longest living mouse strains known, but also has a dramatic delay in the development of cancer. And this is not the only example of this. There's actually many examples of this in nature. So smaller animals tend to live longer and also age much more healthily. That longevity doesn't translate into a human setting. However, that protection against cancer does. So people with Laron syndrome have a defect in the growth hormone receptor. They've actually got a little mutation in the receptor which growth hormone binds to mediate its signals. It's a really rare disorder. There are around 350 cases worldwide, However, the most remarkable thing about people with Laron syndrome is that they very rarely get cancer. In fact, there's only been one case of cancer which has been reported in individuals with Laron syndrome. They also don't get diabetes, and recent studies have suggested that they may have fewer age-related diseases such as Alzheimer's. So this is really quite striking evidence that if we block this growth axis, or this growth hormone axis, very early on in development, that this is actually protecting us against cancer. These types of studies have led us to wonder whether growth hormone is involved in tumour formation, and can we potentially block growth hormone actions as a type of therapeutic strategy. So the first study I'm going to show you was actually carried out in the lab of my previous boss, Peter Lovey, which I did my postdoc in. So in the study we were able to show that around half of breast cancer tumours have detectable levels of growth hormone in their tumours. And you can see this here, I hope you can see this here, in this brown staining in this section taken through a breast tumour. So around half of these tumours are producing growth hormone, and when that growth hormone is detected in these tumours, that is associated with a poorer outcome for patients in terms of reduced survival, and also those tumours are more likely to metastasize and spread. So growth hormone can be detected in tumours, and it's actually the cancer cells which are secreting it. So what's it doing there? There's actually been a whole lot of studies which have looked at this, and these are studies from Peter's lab, our lab, and also some other groups around the world. So I'm going to try and summarise some of these in this slide. Cancer is a disease which is associated with uncontrolled cell growth, and it results from an accumulation of mutations that occur in cells. So normally our cell growth is really tightly regulated, and our cells will detect mutations and they will try to fix them, and if they can't fix them, the cells die off. But some mutations allow cancer cells or cells to grow in an uncontrolled way, and this could eventually lead to a tumour. If that tumour spreads, it has the potential to then form a secondary tumour at distal sites in a process called metastasis. So genetic variation contributes to this process, and mutations contribute to this process. However, hormones can also contribute to this process, and that's because they increase the number of cell divisions cells go through, so they promote their growth. And estrogen does this. It increases the growth of cancer cells. But in a series of studies, we've been able to show that growth hormone also contributes to all stages of this cancer progression. It promotes cell growth, it promotes cell survival, it promotes migration of cells, and it promotes the invasion into local tissues. Another way in which growth hormone contributes to cancer progression is through generating a blood supply to the tumour. Now, normal cell or cancer cells, like normal cells, need nutrients and oxygen to grow, and they need to be able to take away their waste products, and for that they need a blood supply. So cancer cells get around this because they're not going to grow. Tumours don't grow beyond a few millimetres without the attraction of a blood supply into the tumour, and they get around this by secreting growth factors and hormones, which can attract growth of new blood vessels into the tumour. So in an earlier study which was carried out by one of my students, we were able to show that growth hormone is one of these factors which the cancer cells secrete and which is able to promote the growth of new blood vessels into the tumour. And this results in more vascularised tumours, and this process is called angiogenesis. It's also a way that cancer cells can enter into the blood system and then spread throughout the body. So one of the things we've been really interested in is whether growth hormone in the tumours, as we can detect it, is that impacting on some of the therapies which are used to treat breast cancer. And we've done various studies in this area, but I'd just like to touch on some of the work we're doing in radiotherapy. So radiotherapy, of course, is high energy beams which cause massive amount of damage in the cancer cells, massive amounts of DNA damage. And in another study carried out by one of my PhD students, we were able to show that when growth hormone was produced by these cancer cells, that actually protected the cells against damage induced by radiotherapy. And it helped the cells survive following exposure to that. Other labs have gone on to show that growth hormone is actually repairing the DNA damage. So that might be one of the ways it's helping these cancer cells survive. So we were really interested to see if we combined a drug which blocked growth hormone, so a growth hormone inhibitor, and we combined that with radiotherapy, would that actually improve radiotherapy efficiency? And so to look at this, we've carried out a study in mice where we've treated tumours with radiation and combined that with a growth hormone receptor antagonist, which is clinically available. So this is a growth hormone inhibitor. And when we carried this out and used the drug by itself, we found that there was absolutely no effect on the tumour growth. And that's the red and blue line that you're looking at there. This was a little bit disappointing, but there was no effect when we used the drug by itself. This is radiation in green, so when we treat with radiation, we get quite a significant delay and suppression of tumour growth. But the really interesting thing here was when we combined this growth hormone, this radiation with a growth hormone inhibitor, we got a much more pronounced delay in the regrowth of these tumours. So this is actually really interesting. It's the first time it's been shown, and it's interesting because we're not getting an effect with the drug by itself, but when we combine it to radiation, it synergizes and improves the effectiveness of the radiation. So this is something we'd clearly like to follow up. We know that growth hormone is affecting the amount of DNA damage which occurs in the cell, and we think that might be one mechanism that it's doing this. But we also know that that tumour microenvironment can impact on therapeutic outcomes. And we believe that this drug is actually stopping growth hormones secreted by these cancer cells from signalling to some of the other cells in the microenvironment. So we've really been interested in carrying out more of these studies, but one of the most challenging factors in this field has been the fact that we haven't been able to access the drug that we used in those initial studies. And so that's led us to be a little bit more creative, and now we're initiating a program where we're going to develop our own, and we've been carrying this out for the last couple of years. So growth hormone actually works by binding through this little cell surface receptor. This is a big blow-up of a cell. It fits into that receptor like a key into a lock, and it triggers a series of growth signals within the cell. So we're wanting to produce a drug which can block growth hormone from binding to that receptor. And to do that, we've taken 3 strategies. We've just recently completed, or not so recently, but some time ago completed a small molecule screen of over 2,000 compounds, and we were able to identify some growth hormone, a handful of growth hormone blockers from that screen. They're really effective, but they're not very selective, so we're currently working on those to see if we can improve that. Another approach has allowed us to manufacture a drug which is identical in activity to the clinically available one. And so that's going to be a fantastic research tool. And in the last approach, we're generating a monoclonal antibody which can inhibit growth hormone function by binding and blocking the receptor and blocking growth hormone from interacting with it. This is really early stage at the moment, but this third approach is actually looking really promising at this stage. So we've succeeded in making some of the tools that we need to carry on this work, which is really exciting. However, of course, if these are successful, we hope that we will be able to eventually develop them clinically, which would be really exciting. So that's where we're at the moment. And before we finish up, I just think I'd like to come back to some of those risk factors and talk about some of the ways you can think about reducing your risk of getting breast cancer before we finish off. So we know that a quarter of all cancers are preventable through appropriate food, nutrition, and physical activity. And that's around a third of breast cancer. And that can be prevented by modifiable lifestyle factors. So some of these are going to come as no surprise to you. The first of this is diet. So diet's a really interesting one because there's been lots of studies which have looked at the association of diet with breast cancer. And there's lots of different outcomes from these studies. So it's really quite inconclusive. And the best advice we can give you here is to go for a healthy, balanced diet, because eating a poor diet will contribute to this. And this certainly is a risk factor for breast cancer. So weight gain and obesity, particularly post-menopause, is a risk factor for breast cancer. Obesity is linked to 13 different types of cancer, so try and maintain a healthy weight. Unfortunately, alcohol is a key risk factor for breast cancer, and a lot of people are not aware of that, but a very little intake can start increasing your risk of developing breast cancer. Exercise is beneficial. It's extremely beneficial, actually, and it's been shown to reduce breast cancer, but it's also been shown to reduce your risk of 13 other types of cancer. And in fact, it's good at prevention, but it's also excellent during treatment. I don't know if you saw this in the media recently. If we had a pill kit exercise that would be demanded by cancer patients, prescribed by every cancer specialist, and subsidised by government. I can't stress the importance of exercise enough. Of course, if you are a cancer patient and you're thinking about incorporating this into your treatment regime, please talk to your oncologist or specialist and make sure it's appropriate for you. We have an excellent screening program in New Zealand, and we know that if you detect breast cancer earlier, your outcomes are much better. So please take advantage of this free screening program. So finally, I'd just like to thank the team that has been involved in this, particularly my lab currently, in this picture here, also our collaborators, some of them here are the faculty and also those overseas. But I'd particularly like to acknowledge our funding bodies. These funding bodies have supported our work at various stages of the project, and we really appreciate the work that they do and the support that they've given us over the years. Thank you very much.
Thank you, Jo. So we do have time for a few questions, and there is a roving microphone, so if you'd like to ask a question, please just put your hand up and wait for the microphone to come. There's one.
Hi.
Thanks for that. It was really illuminating. I wasn't clear on the reason that you lost access to the growth inhibitor.
So the drug is clinically available, and it's used to treat a condition called acromegaly, which is associated with hypersecretion of growth hormone in adults. So it's not that we've lost access, it's just that it's difficult to get hold of from the company that produces it. And I think a lot of the researchers in the growth hormone field have found this as well. You can end up getting it for 1 or 2 studies, and then it's difficult to get it for applications outside acromegaly or conditions like that. Yeah, it's been really unfortunate. We're not sure. We don't have a clear picture why that's the case. So the drug's off patent now, and we know it's quite tough to manufacture, and it's also extremely expensive to do the sorts of studies that we want to do. So,
Thank you very much for your talk. It was very interesting. Would you recommend for people over the age of whenever it is that the government don't support mammograms to continue to have mammograms?
I think that's probably a good idea. However, unfortunately, not everybody can afford that. But certainly it's certainly worthwhile taking a look at some of the websites, which I actually have. Sorry, I forgot to do that. If you want more information, there's a lot of information on these websites, and making sure that you do regular self-examinations. But I'm not sure what the actual recommendations for that are, but certainly there is potential there to extend that mammogram screening age limit at some stage, and that would be probably very useful.
Thank you. You refer to exercise as being a good thing to do. What form of exercise are you referring to, cardio or resistance training?
So recommendations are cardio, and they're moderate or high impact exercise, and I think for moderate it's 2.5 hours, and for more high impact exercise, so moderate exercise we're talking about brisk walking, so it's about 2.5 hours a week, and for high impact is 1.25 hours over a week. But yes, it is aerobic.
At the front here and then at the back. And then
Thank you for that. That was great. What are your recommendations on soy and soy products with the phytoestrogens?
So that's an interesting one. So we're talking about the environmental estrogens and also estrogens in soy type products, which some people have linked to breast cancer. It's unclear at this stage. However, there is several studies, or quite a few studies now, which are indicating that if anything, it's more likely to be slightly protective rather than a risk for breast cancer. It's not clear at this stage though. It's one of those factors which is still under investigation, and it's not clear why that is. Maybe it competes for estrogen. But at the moment, we don't have a clear answer for that. But the studies are generally on the protective side.
There's a question at the back there.
Well, not protective, reduced.
I've got a question.
All right, well, one here and then last one at the back.
So in terms of growth hormone, so are we going to see any sort of blood screening in terms of, you know, the amounts of growth hormone that people might have, so that we can say, well, you might be in the risk group or something like that?
So it's not clear in terms of whether it's, we believe it's a growth hormone which is produced by the tumour cells rather than our normal levels of it. So screening for growth hormone is also difficult. We've got pulsatile secretion of this hormone from the pituitary gland. But we think the important source of growth hormone is actually coming from the tumour. And studies which were carried out by my boss previously compared that pulsatile secretion of growth hormone from the pituitary to the constant secretion of growth hormone that we have in the tumour, and found that that actually promoted more aggressive characteristics in the tumour cells.
Last question at the back.
You said you had to be creative because you couldn't get the drug for the growth hormone inhibitor. Was that because of financial reasons?
No. It's just because the drug company haven't provided to us the second time. So we've not able. We've applied for it, but they didn't give it to us. And as I said, I think this is quite common across the growth hormone field. Lots of people have been trying to get access to this drug, and it's difficult to get hold of from the company. We don't have a clear answer for that, I'm afraid.
Okay, I'm sure Joe will be happy to answer any further questions afterwards, but we'll move on. Thank you very much, Joe. So our next speaker is Professor David Cameron-Smith, who is Chair of Nutrition at the Liggins Institute and an international expert on nutrition and health. David graduated with a PhD in nutritional biochemistry from Deakin University and did his postdoc at the Royal Prince Alfred in Sydney. He's passionate about food for health and unlocking the science behind it. And although you may be more familiar with David debunking the theory that the All Blacks should get into an ice-cold bath after beating the French, in fact, tonight he's going to talk about how our nutritional needs change as we age and how to avoid some of the unhealthy pitfalls of middle age, about which he knows a lot. Thank you very much.
Navigate my way through here. I should have checked how to do this before. Middle age. Well, there we go. I'm back on track. Right. Inability to use any kind of technology that is not a phone with a dial on it and a pickup. Middle age. I'm just going to go back to the previous speaker and talk very briefly about those canny hormones. I think Joe has done what all laboratory scientists do. They see the forest, they see the complexity, they see the sophistication of the way that evil, devious cancer operates and works. They see all of the nuances in the way in which cancer evades all of the technologies and surgical and radiotherapies that we see today. So while a surgeon or a doctor or a clinician gives you a definitive answer, you will have radiotherapy tomorrow, and it is going to give you a 75% chance of survival. When it comes to laboratory science, Jo is seeing the sophistication of how this operates, and she's trying to understand the details by which cancer evades modern therapy and the best therapy we have. We all know that if you improve therapeutic outcomes by 1%, 5%, 10%, 15%, that the impact on you, me, your loved ones is significant. The number 8 wire approach that Jo has taken is to really re-evaluate the best way to inhibit the growth hormone receptor. That's amazing. She's screened over 2,500 compounds over the course of the last 3 years. She's not only developed one approach, she's developed 3 approaches to inhibiting that growth hormone receptor. And in the process of doing so, she is revolutionising the science by which we are able to interact with that breast cancer cell. And in a Petri dish, she is demonstrating sensational results in the way in which that cancer grows, proliferates, differentiates, invades, and ultimately kills you. I think that's fantastic. And anything that can be done in terms of getting to the root cause, I'm getting off my track, aren't I? Getting to the root cause of doing something positive for every individual with breast cancer and improving the therapeutic outcomes is truly amazing. Now let's talk about midlife crisis, because it's just as severe. So what we will hopefully be doing in terms of my midlife crisis, Frankie's 2.5 months older than me, and I just want to remind him of that fact. So in terms of my midlife crisis, and hopefully your midlife crisis, in fact there should be no crisis, because it's a very important and very significant stage of life where we have a very significant capability to impact on 2 important variables. 1, our longevity, and 2, our quality of life. So let's get serious about improving both of those 2 things and doing what we can do to improve both our quantity and our quality of life. So what is middle age? Well, it's defined in terms of this is the Collins Dictionary defining middle age. It's a period of life where they're no longer... The Collins Dictionary defines middle age as when men start to put weight on around the middle. That's the definition that you find on the internet. There's a warning here. I have a number of jokes, and if you know who the people are who I quote in terms of these jokes, then you are definitely middle age. The first of those is not a joke. I'm the smug man in the middle, and I'm smug because I work with a remarkable team of young scientists. Those young scientists are the people who really bring about the significance and motivation that makes our research possible. Ahana here has had a very tough day, and I really appreciate her for coming along to this evening's talk, and you'll hear from Dr Amber Milan. But each of these people contribute very significantly to our research. If you know who this person is, then that's the first joke. So middle age is when your age starts to show around your middle. And the reason it starts to show around your middle is because it's the period when you're starting to undergo very significant physiological change. And that physiological change is the time period where you are not only changing in terms of who you are, but the environment is starting to have an overwhelming influence. So we are the net result of ancient genes and modern environment. And it's the modern environment that wins every time, no matter how good your genes are, now how beautiful your skin is, now how tall and skinny you are, it is the environment that will overwhelm in the end. And so it's our responsibility to try to fight the environment, and fighting the environment is 2 things. It's taking note of your dietary intake and habits, and it's impacting or doing anything in terms of exercise. The question before is what form of exercise is best? It's what you're doing and a bit more, and a bit more, and a bit more. That's the sophistication of exercise. So this is what we're talking about in terms of midlife crisis and ageing. We know that if you do nothing and you succumb to the environment, then you are heading to this end of the spectrum. That premature death awaits those people who gain weight, who don't exercise, who don't take note of their current circumstances, who will rapidly progress through all of these things. And we know that on the way to premature death, there is poor health and very significant disease. But on the other hand, to make significant adaptations in terms of your lifestyle and to pursue good nutrition, regular exercise, and make wellness a priority, then you are on the pathway towards high-level wellness. And high-level wellness is living a healthy, optimal lifestyle. But in the middle, and that middle is the phase that you exist in terms of midlife, is a period of false wellness. A period of false wellness because you are all sliding slowly, precipitously inevitably, breath by breath, heartbeat by heartbeat, towards one inevitable end. And so what happens now in terms of your midlife is going to have a long-lasting impact in terms of your well-being. And this is an example of successful wellness. 93 years of age, running 100 metres in probably about a minute and a half, but nonetheless participating and living the world as it is. My research team is very focused in terms of muscles, skeletal muscles, because your muscles impact on your functionality, and your functionality is your independence, and your independence is your quality of life, and your quality of life is your ability to go out and experience and enjoy things. You obviously need a few other things along the way, like your marbles, your cognition, but physical activity and muscular strength and muscular function is one of the significant determinants of your quality of life. Let's be really clear about this. Ageing is not a disease. It's a natural consequence of every breath that you breathe. We live in an oxygen-saturated environment, so you generate free radicals from that oxygen-producing process or oxygen-using process. And that process is going to get you. We rust slowly and surely from the inside out. That process of rusting is buttressed or buffered by a whole range of antioxidants. Some of them come from food, most of them come from your physiology, but it is a slow, inevitable process. So it's not a disease, but in your lifetime, it's going to be sold to you as a disease. So while it's not a disease, there are certainly going to be people who tout cures, and it's going to cost you and the New Zealand economy very significantly for you to age. So it's going to become a disease, and it's going to become the disease to have. Anti-ageing therapies will be huge in the course of the next 5 years. And ageing is not this phenomenon. It's something way out in the distance. My 85-year-old mother views people who are 95 as old. People who are 75 view 85 years as old. I view Frank as old. So we always view people 5 to 10 to 15 years older than us as old. No, we are all ageing, and we're all ageing rapidly, and it's this period that we need to make substantive changes in our own lifestyle to impact significantly on our own health. So you might think that there's a lot of research happening in the Liggins and around the place in terms of what's going on early here in life and what's going on late in life. And this midlife is a period where we actually don't do much medical research. Well, that's not true, because here in the middle, we know a lot about what goes wrong in the middle. And there's no doubt that underpinning the most significant causes of premature death is too much middle. It's obesity that drives diabetes, cardiovascular disease, and some cancers, as Joe has described. It's obesity, and consequently there is enormous amounts of research that understands what goes wrong in people who develop diseases. But there's far less research on what you can do to be better, to improve, to increase your wellness. But there is some research. So in terms of increasing and improving your wellness, it starts with these things, your diet, because we all turn over, we're all made of molecules, and that's where we get our molecules from food. And so when we ingest food, those foods are involved in renewing and refreshing every tissue in our body. There's a lot of research in terms of fats, and it reminds you of the very important facts. Saturated fat still remains a very significant component of cardiovascular disease risk. So no, you cannot put your head in a bucket of lard. And no, there is still very significant evidence that tropical oils like coconut oil are not the panacea for long-term health. We know that in terms of carbohydrates, you've got to get your dietary fibre. Number one, dietary fibre. Everybody forgets about dietary fibre. You will eat lentils, you will eat beans, because they're a rich source of protein, they're a rich source of complex carbohydrates and dietary fibre. And alcohol. We used to think in terms of the French paradox. How cute was that? It gave us the liberalisation to drink what we wanted, when we wanted, and how often we wanted to drink it. No, that's a load of rubbish. Over the course of the next 3 to 5 years, there will be increasing headlines that will view your drinking, my drinking, like we viewed smoking in the 1950s and 1960s. Everybody smoked. Therefore, smoking wasn't the cause of this lung cancer stuff. It was the thing that was ubiquitous. We are the ubiquitous drinking generation. And so over the course of the next 3 to 5 years, we'll be looking back going, oh my goodness, how could we ever have finished 3 bottles of wine over the course of a week? A regular kind of standard kind of drinking pattern. But we'll soon discover the dose dependency of alcohol and all of these diseases. Let's get back to muscles. It's important to focus on muscles because muscles are made of protein, and the protein intake in your diet has a significant impact on the turnover of those muscles. But muscles respond to the environment, and the environment is exercise. How much exercise? What type of exercise? Well, definitely more than what most of us are doing now. And any kind of exercise, as often as you can, is better than no exercise. We operate here in the Liggins, and in the Liggins we're very interested in what happens early in life. So early in life, you develop your muscles grow and adapt to the environment. So we have a program of research looking at what happens to muscles and the development of muscles in utero and early in life, and the importance of childhood activity in developing those muscles. And then you reach a peak. When do you reach a peak? I'll show you when you reach a peak in a moment. And then you slowly but precipitously decline. That rate of decline varies. And of course, if you remain physically active, then you can significantly reduce that decline. But if you don't do anything, the rate of decline will get to a point where you achieve or reach a critical threshold, a functional disability threshold. You can't get out of a chair. You can't walk across the room. You can't live independently. You need institutional care. So when we look at a measure of muscle function like muscle strength, you can see that it goes up during early life. So this is thousands of people in lots of different studies. And muscle strength goes up early in life. And when are you at your strongest? Just slightly out of your 20s. And it goes pear-shaped from that point onwards. And it declines slowly and slowly and slowly over the course of your life, and then it accelerates. And it accelerates when you get old and you develop the diseases of age, and those diseases of age impair your ability to be functionally active, and of course the rate of decline accelerates. So we're particularly interested in understanding why some people are up here and some people are down there. And you can see that's a very large spread of people at any given age. So we have a program of research trying to understand 50-year-olds and what makes a big, strong 50-year-old versus a weakling 50-year-old. This is a study that we've just completed. This is kind of this is kind of like the people that we recruit for our studies. I removed Frank's photograph from this presentation, but this is true. We've recruited, each one of these dots is a 50-year-old, between 50 and 52, and each of these dots represents their muscle size, and that's called a cross-sectional area, so that's their girth of their muscle, versus their strength, torque, which is the ability to generate power or force. And for a bunch of 50 to 52-year-olds, you can see that there are fourfold variation in muscle size and threefold variation in muscle strength. So that means in the average 50-year-old, there is tremendous variation. So we have a program of research trying to understand the causes of that variation. And so when we pull out bits of muscle and investigate what's happening in terms of the muscle fibres, so that's the connective tissue, the stuff that does the contracting, and the mitochondria, which is the powerhouse that turns your food energy into contractile energy, you can see from young, middle to old that there really isn't a major difference going on in the factors that we measure. It gets very variable, But there's one important message to take home from this. You're already old when you're 50. You've already got the same patterns of things going on inside your muscle when you are 50 relative to when you are 75. Ageing starts early, and ageing starts early, but only you can now influence the rate of change. So all of us are old. All of us have got old insides. We now need to influence the rate of change. So that rate of change is how rapidly you're declining. And so we're not content with taking people now and then again in 5 years' time. We're interested in accelerating that ageing process. And to accelerate that ageing process, we were really lucky to have a bunch of friends, and that's Fonterra. Fonterra have been a partner in our research program for the last 5 years because while you may know that Fonterra sells milk, it also sells specialty proteins. And those specialty proteins are sold into medical applications. You've seen the ads on television, the ads on television where they're using proteins for rebuilding people. And so there's a very important role for protein and particular types of protein as therapies, as regenerative fuels, as things that we can use to help build and repair tissue. So we've been working on a particular formulation that Fonterra has provided us in a clinical trial. So we're not prepared to let our 50-year-olds get slowly. We want to accelerate their ageing. And so thanks very much for those people who participated in this trial, because we accelerated your ageing by putting you in a leg brace. We held them in a leg brace for 2 weeks. They were not allowed to take that leg brace off. They were not allowed to put weight on their legs. We gave them crutches, and then we also stuck something on them to determine how much they moved. Then we allowed them to move, but we didn't give them any specific advice, and then we put them on a really tough, nasty exercise program. For the smart people, you'll see protein versus placebo, and you'll see that there's no difference between protein and placebo. So magic protein does nothing. There's no evidence that protein in a supplement is going to help you age more gracefully. But what it does show is that when you immobilise someone just for 2 weeks, you get a 5 to 7% reduction in their muscle size and a 20% reduction in muscle strength. And if you do nothing other than just go back to your normal existence, you do not recover. You do not recover fast, and you'll probably never recover. So if you have a cold, a flu, a virus, an injury, a period of immobilisation, thou shalt exercise, because thou shalt not be the same ever again. We've also done other studies where we've fed protein to older men, and this has been a tremendous program of research where we've had many collaborators and many people involved, because we've given older men over the age of 70 all of their meals, and we've been very careful about what we've provided them in terms of protein and vegetables and carbohydrates. And this is a wonderful person involved in our studies. Thank you, if I can't see you. Thank you, Pankaj. Very much involved in developing these meals and providing these meals to our participants. This is what is recommended to you in terms of protein, and this is double what's recommended in terms of protein. If you eat what is recommended for you by the government, you go backwards fast over the course of 10 weeks when it comes to protein. Older people need more protein. You need more protein. You need protein from vegetables, you need protein from dairy, and you may need protein from meat. There's no doubt you need more protein. So you can see that protein increase. Lean mass, that's your muscle mass, increases. And your strength also, we didn't give these guys an exercise program, but your strength also increases if you just adhere to a slightly higher protein diet. Lots of research yet to follow. There is an ageing tsunami, and you can either be part of that wash-up or you can buck the trend. And I certainly hope that all of you will buck the trend and none of you will be lured into the phenomenon of false wellness, day in, day out, doing the same thing. Buck the trend. Do what you can in terms of your nutrition. Do what you can in terms of your lifestyle and physical activity and avoid false wellness so that you are always working towards optimal health. Middle age is not when you're sitting at home on a Saturday night and the telephone rings, and I hope it's not for you. Seize the day, and I thank everybody who's been involved in this clinical research and your time. Thank you.
Thanks very much, David. So we have time for a couple of questions. And whilst the hands are going up, there's a microphone at the front here. Seems that before the next lecture we'll have to have high-fibre bread and water.
Hi, thank you. I exercise an enormous amount, but all of it is walking, and I worry, should I be making sure I have resistance exercise as well?
There's no doubt that walking, sustained physical activity that has an aerobic component, is the base. And you need to build from the base. And so you are correct. You have to load, you have to apply pressure, torque, strain to your muscles. And you have to do so in a way that's going to result in some degree of muscle soreness, because that muscle soreness is a necessary component of rebuilding and repairing and activating the growth pathways. That doesn't mean you should be a hobbled, cobbled mess, but it does mean that you need to do it on a regular basis. 2 to 3 times a week is what we understand in terms of optimal, and it doesn't have to be a gym. It can be pulling weeds out of the garden. It can be lifting things around the house, and I'm sure you're already doing it to a far greater extent than you're probably aware of. But congratulations for walking so much. A lot of people don't.
I'm interested in the alcohol one. Since 1966, my wife and I have been drinking about 1 3/4 bottles of wine between us a week. In other words, 1 glass of wine with the main meal. This is not excessive consumption, but I think it's great for well-being. Would you agree?
I would be incorrect to say no. That indeed what you are consuming is good for wellness. But I want to make a number of important points. Your 1 3/4 or 1 1/4 bottle over the course of a week is probably more significant than what's ever been consumed by any population at any point in the past, except for the Victorians, and the Victorians dropped off the perch nice and quickly. So. The Victorian aristocracy. So the evidence is that there is no. So it's a bell-shaped curve in terms of alcohol. We know that a standard drink per day, probably through to 1.5 standard drinks per day, is not going to do you any harm. The question is, how much is a standard drink? A standard drink is 125 mils. Do you know how little 125 mils is? It's not very much. 125 mils per night, pushing up to 200 maximum.
Okay, we've got one last question, and then we'll move on.
Just with the alcohol again. When you talk about a standard drink, are you talking about a standard drink being the same measure of alcohol for a man or a woman, and depending on their size?
A standard drink is defined in terms of the grams of ethanol, 10 grams of ethanol, and so I'm talking about men and women, big and tall. There is clearly a distribution difference. So a man has about 2 extra litres of blood, and of course that's going to reduce the concentration and the load. And so we can get nuanced in terms of the amount of alcohol, but we do still talk in terms of standard drinks, 10 grams of ethanol. Yes.
Thank you very much, David. So our final speaker this evening is Dr Amber Milan, who you'll very quickly realise is a very long way from middle age. She's interested in the biochemical processes that are triggered as we digest food, and in particular how these processes change as we age. So Amber studied biopharmaceutical sciences at the University of Ottawa before completing her BSc in nutrition at Acadia University in Nova Scotia and her PhD here at the Liggins Institute with Professor David Cameron-Smith. So in this talk today, Amber will present her latest research into different types of dairy intolerance and the process of identifying the specific components of our food that cause problems, and to explain how intolerance can fluctuate over time and what our genes or our gut microbiome might have to do with it. Thank you very much, Amber.
So David, I think, has laid out why the nutrition that we have as we get older is really important, and that's definitely something that I'm interested in. But tonight, I'll be talking a little bit more about our relationship with food and how we might make choices that might affect our health. So allergies or intolerances are something that really can have a huge impact on what we choose to eat and our health, but they do so in slightly different ways. So allergies, we know, are caused by an immune response to a food component, and usually this is a protein, and I've just indicated a few common allergens right there. And this affects more children than it does adults, so there is changes with the way that the immune system responds to these foods, and we know that these are quite severe reactions, and the response for people who have these is really just to eliminate those foods from their diet. But intolerances, on the other hand, are quite different. They don't have the same immune responses that we have with allergies. And they're also caused by a variety of other different foods. And so it's estimated that maybe half of the population might experience an intolerance. But in actual fact, I think we don't really know how many people experience an intolerance because we don't understand the underlying causes to a lot of these, or how to diagnose it, or how to go about treating it. And so here are some common food intolerance culprits. And we also understand that what's causing intolerance in each of these foods might be very different. So it could be a sugar, like lactose is in dairy products. It could be a protein, like we have in gluten, in wheat products. Or it could also just be other naturally occurring or added chemicals that are in foods. So for someone with a food intolerance, what does this mean? You can eliminate the food from your diet and go about your life. And that may be an option because we have a lot of alternatives available. So for common food allergens like dairy or gluten, there's lots of options. And it may be a bit confusing to know which one is the best option. And there also may be some economical costs to that. So this may be quite a cost burden for some people. But in addition to that, if we look at all the different types of intolerances that we may experience, add in the food allergens that we know of, and look at also food preferences or the current food fads, very quickly you can look at a menu and be a little bit perplexed about what to order or what to bring to your next dinner party. And so for someone who has a food intolerance, also not understanding what it is that's causing them intolerance can have a pretty big social impact on their lives. And it can really affect quality of life. So in addition to those consequences of eliminating foods from our diet, what else might we be concerned about? So I'm going to be talking about milk because that's what a lot of the research that I've done is focused on. But I think a lot of the things that I'm talking about can be applied to a lot of other intolerances that we may know about or not really know much about. So there are also health consequences that we need to be aware of. And so for something like dairy, if you eliminate dairy from your diet, you're also eliminating something that's really widespread in our food environment and is quite an important nutrient source for many people, particularly for children or the elderly. And as David pointed out, something like protein is quite an important thing to make sure that we're getting in our lives, particularly as we get older. And dairy also has a lot of other essential nutrients that can be quite difficult to get from other food sources. Things like calcium we know is really important for bone health, and making sure we get enough calcium can also help to promote bone health as we get older. And dairy consumption has also been linked to prevention of a few chronic diseases, which can be quite important. But for something like calcium, we can obviously get that from other foods. So if we eliminate dairy, then we just need to have alternatives, right? Well, the problem is that not all foods are going to be able to give you the same amount of those nutrients that you may need. So for something like calcium, if we have a glass of milk, to get the amount of calcium in a glass of milk from other foods that are really rich in calcium, like spinach or kidney beans, you need to eat a lot of that food. And so these portion sizes are probably unrealistic for the average person. And so if you're not getting calcium from milk, you need to be really aware of what you are getting your calcium from. And someone that doesn't have necessarily a balanced diet may not be meeting those needs. So by eliminating foods from our diet, we may actually be putting ourselves at risk for health consequences. So why might somebody avoid dairy? Well, we know that lactose intolerance is probably the main reason that someone might avoid dairy in their daily lives. So lactose, as I mentioned, is a sugar that's in milk. And that sugar, when it's digested, is broken down in the intestines by an enzyme called lactase. So that lactase breaks the lactose into two sugars, and then those sugars, glucose and galactose, can be absorbed for energy. But in someone who is lactose intolerant, that lactose doesn't get digested because they don't have the enzyme required to digest that sugar. So instead, that lactose moves through to the large intestine where the gut bacteria are able to digest that for the person. But this results in a bacterial fermentation, and the result of that digestion by those bacteria produces a lot of different byproducts. So it produces gases, short-chain fatty acids, and these byproducts are what cause the symptoms of lactose intolerance. So a lot of the symptoms would be something like cramping or bloating, diarrhea, and also flatulence or gas. One good thing about this, if there's a good thing, is that that gas means that we actually have an understanding of what's going on with lactose intolerance. And that gas that's produced, we can actually measure it. So you exhale it when you breathe. And so for someone who's lactose intolerant, we can measure the amount of gas that they're breathing out. And we can actually identify, yes, it is lactose that you are intolerant to. So that's quite helpful for lactose intolerance. But why do we even get lactose intolerance, and who has lactose intolerance? Well, lactose is also the sugar in breast milk, and so essentially every infant that's born has the ability to digest lactose. So why are some people lactose intolerant? Well, as we get older, so not even that much older, but just from infancy to toddlerhood, as infants get older, they start to consume other foods, and the body naturally will decrease the amount of lactase that it's producing. So the amount of lactose that can be digested will decrease. And it's thought that this is actually an evolutionary adaptation, so that toddlers will stop drinking breast milk and the subsequent infant has a better chance of survival. So in fact, this happens in all mammals. So all mammals will be lactose intolerant by the time they reach adulthood. The reason that humans are not lactose intolerant is because somewhere along the way, some humans have developed a genetic change to that lactase gene. So normally that gene would be turned off when you become an adult, but for some people, that gene stays turned on. So who are these amazing people? So if we look at who's lactose intolerant throughout the world, we notice that we have very low rates of lactose intolerance in regions of the world that have traditionally consumed a lot of dairy. So it's thought that this mutation or this change in the ability to digest lactose happens somewhere in the northern regions of the world. But this map is just based on what we know about the genetics, and we actually don't know that much, surprisingly. And the National Institutes of Health has actually recognized that we don't know anything about how many people have lactose intolerance. And the reason for that is that it hasn't been systematically studied. As an example, in New Zealand, there's only one study that I was able to find that's actually looked at this. And this was in Christchurch, and they estimate that about 8% of the population is lactose intolerant. But what we need to consider is that someplace like Christchurch has a very different demographic population than someplace like Auckland. And so some of those regions in the world where we know that a lot of people are lactose intolerant, that might not be reflected. The other thing is some regions haven't even been tested. So what we know about Maori and Pacifica peoples and their rates of lactose intolerance is very, very little. That same study had only 30 people that it was able to look at the rates of lactose intolerance in Maori and Pacifica. And it estimates that probably about 30% of people may be lactose intolerant. So I think what we do know about who's lactose intolerant is that it does vary depending on your ethnicity and your background. But that we don't have a really good picture of the problem, and it may actually be contributing to some disparities in health that we should be aware of. So if someone has lactose intolerance, what can they do about it? Do they avoid dairy and put themselves at these social, economic, or health risks? Well, there are some solutions and ways to manage lactose intolerance. So avoiding lactose is a really great solution. So there are lactose-free products that can be consumed, or you can also take the enzyme to be able to digest that lactose. But these are kind of short-term solutions, and it still will lead you eliminating dairy from your diet. You can also have less lactose. So we know that people who have lactose intolerance can digest a little bit of lactose at a time. And so by choosing foods that don't have much lactose, like cheese or yogurt, then people who are lactose intolerant can still consume dairy. Or even just having smaller amounts of lactose at a time can help. additionally, if we spread that lactose intake throughout the day, then this can also help to manage those symptoms of intolerance. But those are just ways to manage it. What if we could change the ability to tolerate lactose in people who no longer can tolerate lactose? So what we've recognized, the National Institutes of Health has also recognized that there are people who can't absorb lactose, so they malabsorb lactose, but they're not necessarily intolerant. So not every person who can't digest it is going to feel the same symptoms of intolerance. And we don't quite understand why, but one solution might be the gut microbiome. So we know that the gut microbiome has a really big impact on our health, and I think we're understanding that more and more. And we also know that the gut microbiome is quite important for the digestion of lactose in someone who can't digest it themselves. That's what's producing all of the side effects that they're experiencing. And we also know that if you can change that gut microbiome to types of bacteria that can better able digest that lactose or to digest the byproducts of lactose malabsorption, then people who have lactose intolerance can actually tolerate lactose much better. So there is the possibility to be able to change the way that someone can tolerate lactose. So the way that we would do that would be two different factors. So we can actually change those gut bacteria directly. So if we provide these bacteria in the forms of probiotics, so foods that already have these bacteria, so those would be fermented foods like yogurt or potentially other fermented foods. But we could also help to feed those bacteria that we already have in our gut. So this would be through the use of prebiotics. So these prebiotics are the undigestible fibers that we can't digest, but that the bacteria are able to grow on. So these would be fiber, but in fact, for someone with lactose intolerance, lactose would actually be a prebiotic. So if it's not lactose intolerance for everybody, then what might it be? We know that not everybody who reports having a problem with milk is lactose intolerant. There's a large number of people who self-report that they have a problem with milk, go for a lactose test, and it turns out that they're not intolerant to lactose at all. And importantly for these people, if they eliminate lactose from their diet, if they go on to something like a lactose-free milk, it's not going to help them. So they're still going to experience the same discomfort that they experience with the lactose. And so what might it be for these people if it's not lactose intolerance? Well, we know that there are lots of different components, nutritional components in milk. So there are a few different options that we might be able to look into. Protein is a major component of milk, and dairy protein has a lot of different proteins that are contained within it. Some of these are allergens, but there are lots of different types. We also know that different species produce different types of protein in their milk. But even within the same species, the type of protein that's in the milk can also be different. So this is beta-casein here that comprises about 30% of milk. And we know that in cows, most of them will have a combination of two different types of beta-casein, the A1 and the A2 type of beta-casein. Originally, it's thought that all cows only produce the A2 version of the beta-casein, and then at some point along the way, some cows started to produce the A1 version. And so these proteins are pretty much the same, but they differ just slightly. And that difference actually changes the way that they're digested. So when they're digested, they form different products. And what we know is that the A1 beta-casein, when it's digested, it produces a peptide, which then interacts with receptors in the gut. And these receptors also initiate an immune response or an inflammatory response. And so it's thought that this peptide causing this immune response may actually be responsible for some of the discomfort that people feel when they drink milk. But this hasn't really been studied very well in humans, so we don't really understand whether this is the cause of a dairy intolerance that's not related to lactose. So what we did was we did a study to try to look at whether we could identify what were those symptoms that people with a dairy intolerance experienced that wasn't caused by lactose, and whether changing the protein in the milk had any effect on the symptoms that they experienced. So we took a large cohort of women who said that they had a problem with milk, and we tested to see whether they were intolerant to lactose. So we had one group of women who, when we gave them lactose, They had all the symptoms that we would expect them to have, and one group of women who, when we did give them lactose, they didn't experience any symptoms. So we know they think they have a problem with milk, but it's not lactose that's their problem. And so what we went on to do was then give them a large dose of milk. So we wanted to make sure that we really understood what this discomfort was that they were feeling. And so we gave them 3 glasses of milk all to drink. And with people who had lactose intolerance, when they drank milk, they again experienced all the symptoms that we would expect when they consume lactose. So they felt cramping and bloating and gas. But with the women who didn't have lactose intolerance, they experienced a completely different set of symptoms. So they still had bloating and gas, but they also experienced some upper GI issues, so they had more reflux, which wasn't experienced in people with lactose intolerance. The other really notable thing was that the way that these symptoms were experienced was completely different. For people with lactose intolerance, it took a while for these symptoms to happen, which makes sense because the lactose takes a while to get down to the large intestine and cause its effects. But for people with dairy intolerance, these symptoms were really, really quick. So they felt really horrible, really, really quickly. So the biggest question here was, is it the protein? If we change the protein, does this help people who have dairy intolerance? Well, unfortunately, the answer was that when we changed the protein, so if we provided them A2 milk, which didn't have any of that A1 beta casein, they still felt just as horrible. So from this research, we haven't actually shown whether it's the A1 beta casein that causes dairy intolerance. So what we're doing is undertaking another study to see whether if we change the species that the milk is produced from, whether this has an effect on dairy intolerance. So we'd like to look at whether sheep milk has an effect or a difference, if it's digested differently or tolerated differently in people who have dairy intolerance. So we're currently recruiting for this study. If you know anybody who thinks that they have a problem with milk, they can find out more about the study through the Liggins website, or you can also send me an email. From that first study, we also wanted to understand whether the protein had an effect with the lactose, or whether it was just lactose that might cause intolerance to people who have lactose intolerance. So we did this by looking at whether we changed the protein, if that had an effect on people with lactose intolerance to be able to tolerate milk. And we also looked at what the effect of just lactose was. So if we remove the lactose from milk, is there any difference? As expected, with regular milk, which has lactose, has the A1 beta casein as well as A2, people with lactose intolerance had a bad time. And when we removed the lactose, they had a much better time. So most of the symptoms associated with lactose intolerance were removed. Bloating is still here, but I think that's probably due to us asking them to drink 3 full glasses of milk all at once. But interestingly, when we changed the protein and we had lactose still in the milk but no A1 beta casein, we actually saw a reduction in some of the symptoms that they experienced. So although they still had bloating and gas and some cramps and pain, they didn't experience some of these more severe symptoms. So they didn't have nausea and they didn't have to go to the toilet as urgently. So just by changing the protein, we were able to change their ability to at least tolerate that lactose in a really short period of time. I think we don't quite understand what it is about changing the protein that changes the symptoms, but we do know that it's a bit multifaceted. And if there is an immune response, then we may need to look into this a little bit further. So what we're doing is another study where we're looking at whether those inflammatory responses that may be caused by the A1 beta casein can be changed over the course of 2 weeks. So we'll be comparing whether consuming regular milk or the A2 milk has an effect on that inflammation, and if we can remove that inflammation, whether we can reduce the symptoms of lactose intolerance. But there's also other mechanisms that might be at play here. So we know that the gut bacteria that help to digest lactose in people who have lactose intolerance can be affected by consuming lactose. So what we've done is we want to look at what the protein is doing to those gut microbes. And so in addition to feeding these women milk, we're also feeding them cheese, which doesn't have lactose. So this way we can actually look to see whether the protein as well as the lactose has an effect on that gut microbiome and whether we can change their ability to tolerate lactose. So what's next for all of this? I think I've probably raised more questions than I've answered about what it is that causes us intolerance, but I think that's really the key issue. I think we don't understand very well what causes intolerance. There may be some kind of an immune response that we're not really clear. It might not be exactly like an allergy response, but there may be some immune involvement, and that may be also through inflammatory pathways. So there may be inflammation that we're dealing with too. But as I've mentioned, there also seems to be interaction with the gut microbiome and potentially other disorders, gastrointestinal disorders that we may experience. The next step, I think, for clinicians and also for researchers is to understand how we can diagnose intolerances. At the moment, for people who have an intolerance, the solution is usually to just stop eating the food that is causing them discomfort. And I think it's also difficult to identify what that food is sometimes. So what we're doing in our research is using the cutting-edge technologies that we've got available at the Liggins to be able to measure the chemicals, the molecules, and the metabolites that happen and are measurable in the body in various different body fluids after a trigger food is eaten. And hopefully we can try to identify signatures of these chemicals that can help us to identify people who have an intolerance to a specific food and maybe even identify what the root cause is. But ultimately, for myself, the goal of the research is really to understand how we can provide solutions to people. So what can we do to help people change the way that they're choosing their foods or change the way that they experience their foods to help their overall well-being? So I'd just like to acknowledge, finally, all of the funding bodies that have supported this research. I'd like to thank the team that's been involved in conducting all these really, really tough studies. And I'd also really like to thank the participants that have participated in these studies. We're asking people who have an intolerance, a known intolerance, to come in and eat that food that causes them a lot of trouble. And we're asking them to do it in sometimes some unreasonable quantities. And I just really thank their participation because we couldn't do it without them. Thank you.